Hello and welcome to this presentation about computer vision in healthcare, saving lives with AI. My name is Branislav Hollander and I will try to guide you a little bit through this field and show you what's out there and how you can get into the field. Let's start a little bit about myself. I studied physics and biomedical engineering at the Technical University of Vienna in Austria. I've a bit more than 6 years of experience with image processing and computer vision, mostly in the medical field. Currently, I'm employed as a senior software and machine learning engineer at PIUR Imaging. PIUR Imaging is a company that's set to revolutionize 3D ultrasound scanning with AI and machine learning techniques. And I'm also enthusiastic about writing a blog about AI and computer vision in general. So let's jump right into the topic. And the first thing you might ask yourself is, why use computer vision in healthcare? Well, as you know, in healthcare you have a lot of imaging modalities, a lot of treatment are diagnosed, a lot of diseases are diagnosed with imaging. And often what happens is that the radiologist or other doctor does an image, as you can see here on the left side. For example, this is an ultrasound image of the thyroid. Of course, he has to be trained to do this and skilled and know where to do the image and how to set up the machine. And then he does some measurements here, as you see here with the crosses, and he looks at some table. For example, on the right hand side you have the so-called TI-RADS score table, which is something like a table which tells you look at a thyroid nodule, so this would be a thyroid nodule, and then depending on its specific characteristics, for example, compositions, echogenicity, is it bright or dark in the image, what's its shape, how does the margin look, and so on. He evaluates these things, and then depending on how many points he assigns to the image, this is either benign, mildly suspicious, or even highly suspicious and can basically indicate cancer. So this is something that is happening daily for radiologists. This is what reading is about. And now let's look at the side of computer vision. Well, computer vision trains the computers to see the world as humans do. That's the idea of computer vision. And computers are particularly good at pattern recognition. So when they see a pattern in the image, they will recognize it. And this is exactly what's happening in this image that you had before. You have a pattern, which is this nodule delineated by this dark shadow here, and you have to detect it. And this is what the computer is very good at. And the computer is also very good at placing these calipers here to do the measurement afterwards, of course. And what does it bring? Well, if you have an AI system which is running on the computer automatically, of course it helps with the speed and accuracy of the diagnosis, in particular if it has competitive performance with human-like performance, which for some tasks it's already the case actually. And of course it also lowers the burden on the clinicians, because it just helps them to detect the features that they need. And as I said, tasks like classification, detection, or segmentation often approach human-like performance, and these tasks are actually the main tasks in the whole of computer vision. So let's have maybe a look what specifically they are. So here in this slide you have three classes of images. In A you see an example of classification. So you have three images here, COC1, COC2 and COC3. These are MRI images of the brain, of a tumor in the brain, presumably, and you need to classify these according to some class of the tumor. So if you look at this thyroid score before, you see you would basically classify it from benign to highly suspicious. You would have 5 classes, and in this case you have 3, where this is a tumor that is very widespread, and this is a tumor which is localized. In B, you have an example of segmentation here. So segmentation is something much more accurate. It doesn't only tell you the class or how the disease is classified, but it tells you the exact location of the disease, delineated by this red curve here, you see. And for this task, for example, it seems it's rather easy to delineate the structure here, but the problem is if you take I don't know, 3 or 5 physicians and give them the same job, which is actually what you do for the ground truth data for the machine learning algorithm, they will often draw completely different curves here. So this is an issue that we might have to deal with also in training the algorithms. And we don't exactly know what the ground truth is. And in C, you have an example of detection. So for a change, this is an ultrasound image here of the thyroid again. And detection is something a little bit more coarse than segmentation. You see, this is also a nodule that we're looking at here. And you only need in detection to draw a bounding box, a red bounding box around the structure that you want to look at. So how does this actually work? Well, in computer vision nowadays, the most widely used machine learning model are so-called convolutional neural networks, and this is part of deep learning. These networks, these are neural networks which consist of convolutional and pooling layers. So just to explain a little bit further, we'll go into this a little bit more into the detail in a short while, but as you see in the image here, well, you have basically 2 kinds of operations. You have convolutions here, and then these convolutions are usually followed up by which they call subsampling here or pooling. And again, convolution, subsampling, and then you have something which is called fully connected layer, which just basically collapses the image into the final output. So for example, the output could be, if you have a classification, the output could be the class of the image. It could also be for segmentation another image, which a label map, which just tells you for every pixel here if, for example, this is a robot or not. So it would nicely delineate this robot if everything works well. And this whole structure, which can be huge and can have millions and millions and billions probably of parameters, this is trained using gradient descent. So maybe a little bit more explanation about what is convolution. Just look at this matrix on the left side. This is called the convolutional kernel here, and as you can see, this is a 3x3 matrix in this case. It's not restricted to that, but this is in this example. And you have some numbers in this matrix. And these numbers, these are so-called weights of this kernel. And then you have in blue the image, which is also a matrix, in this case a 5x5 matrix, a very small image. And what you do in convolution is you take this kernel here, which is 3x3, and you slide it across the whole image like this. And in every step, you multiply the number in the kernel by the number in the image, by the intensity in the image, like this. And then you add them all up. So in this case, for example, for this part, you would get 12. And then if you move, you get 12, 17, and so on. And so this green thing is the output. And as you can see, the output is also smaller than the image because on the borders, you cannot slide the kernel across the border because here you have no values. But there is a technique called padding where you basically pad the image, for example, by zeros, where you can alleviate this issue. Now, pooling is something even simpler. What you do in pooling is you also slide, for example, a 3x3 kernel through the image, but what you do is you don't have no weights, you just take the maximum of every 3x3 matrix. So here the maximum is 3, here the maximum is 3 again, and for example in this one the maximum is 2, so the output will be 2. And these are the two main operations in convolutional neural networks, and that's how the whole stuff works roughly. Of course, this is just an overview. So how do we train such a CNN in particular? Well, it's quite a complicated process because this is an iterative process. As you can see, there are two iterative loops here. So first of all, you get some raw data here. And what you do afterwards is you apply some pre-processing to the data. For example, you might have to change the contrast, normalize the intensity, stuff like that. And then you have the prepared data and you apply your machine learning algorithm to that, your model that you've chosen beforehand. And then you see, well, this model doesn't perform as well as I wanted it to. So then you iterate here to find the best model. So you improve on the model, usually by a trial and error approach, and until you find a model which works well for you. And then finally you can deploy the chosen model and have it in an application. So let us now jump to what are the challenges in this computer vision, because until now I've told you everything is great, and we can, in healthcare, we can use it and be happy about it, and it works well and the clinicians are all happy. But in reality there are a lot of issues. One issue is data collection. So here in this graph you have in a timeline here, the most used data sets in computer vision. And for example, I want to focus your attention on this ImageNet dataset, which is from roughly 2010, and this contains something like, I don't know, maybe 10 millions of images. And so this is a lot. There is also an ImageNet 10K, which is even higher. This contains actually 10 millions of images here. And these datasets are huge, and this is what deep learning, or CNNs in particular, require to achieve good performance. Unfortunately, if you look at a standard healthcare dataset, this is usually much smaller, maybe around 1,000 to 10,000 images or samples. And this is of course a big issue because this deep learning model won't work as well with this small number of examples, and moreover, if these examples don't have sufficient variety, so for example they were all acquired at one center on one patient or one device, stuff like that, then it won't work well, it won't generalize well to other centers or patients. So this is one of the big issues here. The other issue is bias, and this is a very nice example, I think, of how bias works. It's not from medical imaging, but it's from computer vision. So this is an algorithm which is was a machine learning algorithm trained on the ImageNet dataset. This is this huge dataset that I showed you before, yeah? And even this one has a lot of bias in it. So what's the bias? You just have a look at this. I mean, this is clearly a picture of a footballer. This is also a picture of a footballer, This is a picture of an ice hockey fan. This is a picture of an athlete, I guess. This is a picture of a boxer, and this is a picture of a footballer again. Now, what's the problem? They were all classified as basketball. Why? Well, because these are black people. And the problem is it's not that the computer or the algorithm itself is biased against black people. It's that the data set itself contains mostly images of black people playing basketball, because that's the cliche. And in this case, it's similar. You see, there are Asian people here playing football, but they were all classified as ping pong. You see, there is a guy playing ice hockey, but he was classified as a baseball player, and this is something that is an issue in machine learning in general, and in healthcare in particular, because if you are biased, for example, against some specific disease type, and you cannot really see the other disease nicely, then you will have a problem out in the open in the practical usage of your algorithm. So let us now maybe look at an example from computer vision in medicine. There are two examples that I want to show you. The first one is from my own company, PIUR Imaging, and it's about vessel detection in 3D ultrasound. So this is our application in PIUR Tools, and as you can see, this is a 3D ultrasound volume. This is the rendering of this volume here. And on the right side, you've got the ultrasound frames, which are very nicely visualized here in the application, and some slices through the application. And you can see also the visualization of the probe, how the probe is moving. In this particular case, we can scroll through the data set. And in this particular case, we are looking at the lower leg. And as you can see, we were tracking the vessel, the main vessel of the lower leg, which is this dark structure, this dark ring structure in the image. And what we wanted to do in the AI algorithm is to detect this vessel and visualize it nicely in the lower leg. So let us maybe now look at what the algorithm can do. And as you can see, this is what the algorithm did. It nicely segmented, this is a segmentation problem, it nicely segmented out the vessel in the image. We can scroll through it and we can see how it nicely tracks the vessel. We can even rotate it here like this, and we can see that it branches out nicely. And this is very valuable information for the surgeon, for example, for the vascular surgeon. If he wants to perform a vascular surgery, then he needs to know how the vessel is looking underneath the skin, and he also needs to see the branches if he wants to, for example, remove one of them. Another example that I wanted to show you is actually this previous example was more a visualization example. This is really a automated diagnosis example. This is a breast cancer detection system developed by Google to detect breast lesions in mammograms, which is what usually radiologists do. And this algorithm was trained on a huge data set, actually on two data sets. One was from the UK, 25,856 patients, and it was tested on a US data set, 3,097 patients, basically to assess the bias, if there is any bias on the UK data set, which would not translate to the US data set. And this whole study was claimed to be a huge success because the whole system was reported to be more accurate than individual radiologists. They actually gave a part of the data set to 6 different radiologists, and there were some lesions, and this is the A part of the image here. This is a lesion that the AI system detected and none of the radiologists actually saw. Although there is still an issue, there is this B image, which is actually the opposite case. That's a lesion that all 6 of the radiologists detected correctly and the algorithm did not. So it seems that the algorithm is more accurate than individual radiologists, but it sees something different than what the radiologists see. And this suggests also, that's the conclusion of this huge study, that the best thing to do, and this is also what happens in practice, is to use this system in tandem with human readers. So one possibility, for example, is that the system pre-detects some areas to look at for the radiologist, and the radiologist then decides himself if that is a lesion or not. But of course, usually the radiologist still has the main and the last word on the diagnosis. So with that, I arrived slowly at the end of my presentation. The key takeaways from my presentation that I want to take home with you is that, first of all, computer vision is transforming medical imaging. This is undisputed, it will come, it's already coming, it's already used in practice. If it's used correctly, it benefits both healthcare professionals and the patients because it makes everything faster, it makes everything more accurate. What you have to beware of is consistent bias, as we saw in the slide before. There are already many applications out there, so if you go to a physician and you get a MRI done or CT done, there is a great chance that some AI algorithm will run over your images. And the most important thing from my whole presentation is that medical AI is really exciting, and I think it has a great future. And we want you for medical AI. Thank you for your attention.